the idea of a journey. There is a thought experiment that astronomers sometimes pose to students, not to be answered, but to be felt. Imagine you could travel, not in the way that humans travel, not aboard rockets burning through carefully calculated orbits at tens of thousands of miles per hour, but freely, effortlessly, at any speed you chose. Imagine you could simply go. What would you encounter if you pointed yourself outward and kept moving? The question sounds simple, but it is not. Even with perfect freedom of motion, crossing the observable universe would take you past structures of such extraordinary variety. Galaxies spinning slowly in their billions of suns, galaxies colliding in slow-motion catastrophes that last hundreds of millions of years, places so empty that you could travel for hundreds of millions of light years and find almost nothing. That describing the journey requires more than a list of distances and objects. It requires understanding what a galaxy actually is, how they arrange themselves across the cosmos, and what the universe has been doing for nearly 14 billion years to produce the landscape we would find ourselves flying through. This is that journey. Not a physical journey, not yet, and perhaps not ever, but an honest one, grounded in what we actually know. What instruments like the James Webb Space Telescope and massive ground-based surveys have revealed, and what the universe itself has written into its own structure. We start at home because it is the only place we know in detail. Leaving the Milky Way. Our own galaxy, the Milky Way, is as good a starting point as any because it is the only galaxy we will ever be able to study from within. That insider perspective comes with a strange disadvantage. Because we sit inside the disk of the Milky Way, about halfway out from the center along one of its spiral arms, we see our own galaxy in a way we cannot see any other, edge-on, foreshortened, and obscured by 100,000 light-years of its own gas and dust. The bright band of the Milky Way that stretches across a dark sky night is simply our view down the plane of that disk. A disk so thick with stars and interstellar material that the center of our galaxy is invisible to optical telescopes. Only in infrared and radio light can we see through to the galactic core. What we have pieced together from that constrained vantage point is a barred spiral galaxy, a common type, but by no means a small one. The disk of the Milky Way stretches roughly 100,000 light-years across, with a central bar of stars roughly 27,000 light-years in length running through the middle. 4 major spiral arms wrap around this bar, trailing arcs of young hot stars, glowing gas clouds, and active star formation regions. Our solar system sits in a minor arm called the Orion Spur, about 26,000 light-years from the galactic center. The entire disk rotates. Our solar system completes one orbit of the galactic center roughly every 225 million years, a period sometimes called a cosmic year. At the center of that rotation sits Sagittarius A star, a supermassive black hole with a mass around 4 million times that of the Sun. Every galaxy we will encounter on this journey has its own version of this central engine, ranging from the modest to the almost incomprehensibly massive. Above and below the disk, the Milky Way is surrounded by a diffuse spherical halo of ancient stars and globular clusters. The remnants of the galaxy's earliest phases, formed before the disk even existed. And beyond the visible stars, extending much farther than any light reveals, lies an enormous halo of dark matter. This invisible scaffold of mass is thought to extend out hundreds of thousands of light years, and it outweighs all the stars in the Milky Way many times over. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range reflects genuine uncertainty. Counting stars in your own galaxy from the inside is nearly as difficult as counting trees in a forest while standing inside it. Some estimates push the number higher. It is home to hundreds of billions of planets, with the rocky ones potentially in the billions, and it contains enough interstellar gas and dust to keep making new stars for billions of years to come. By the standards of the universe, none of this is extraordinary. The Milky Way is a large spiral, solidly above average in mass, but far from the largest thing out there. As we leave it behind and begin our journey outward, we should remember that for most of human history, this galaxy was the entire known universe. The local group. Moving outward from the Milky Way, the first thing we encounter is not open space, but company. The Milky Way is not alone. It belongs to a gravitationally bound collection of galaxies called the local group, and understanding this collection reveals something important about how galaxies are distributed throughout the universe. Almost none of them are truly isolated. Gravity, given enough time, tends to gather things together. The local group spans roughly 10 million light-years across. At its heart are two dominant galaxies, the Milky Way and Andromeda, known formally as Messier 31. Andromeda is the largest galaxy in the local group, a spiral somewhat more massive than our own, containing roughly 1 trillion stars. It sits about 2.5 million light-years away, so close that on a clear dark night from Earth, it is visible to the naked eye as a faint smudge in the constellation Andromeda, making it one of the most distant objects a human can see without any optical aid. The light reaching our eyes from Andromeda left that galaxy 2.5 million years ago, before anatomically modern humans walked the Earth. Andromeda and the Milky Way are approaching each other. The speed is modest by cosmic standards, about 110 kilometers per second, but the direction is unmistakable. In roughly 4 to 5 billion years, the two galaxies will begin to merge, passing through each other in a slow gravitational catastrophe. Stars almost certainly will not collide. The distances between individual stars are so vast that even during a galactic merger, actual stellar collisions are rare. But orbits will be scrambled. The disk structure of both galaxies will be disrupted. Gas will be compressed into waves of star formation. Over the following 1 billion or 2 years, the two galaxies will merge into a single, larger elliptical galaxy that astronomers have informally nicknamed Milkomeda. Our solar system will likely survive, but in a completely different orbit, far from anything resembling our current neighborhood. The third significant galaxy in the local group is Triangulum, Messier 33, a spiral about 3 million light-years away and considerably smaller than either the Milky Way or Andromeda. Beyond these three, the local group is populated mostly by dwarf galaxies, dozens of them, many discovered only in recent decades as surveys became sensitive enough to detect faint, diffuse systems. The Milky Way has its own collection of satellite galaxies, the most prominent being the Large and Small Magellanic Clouds, which are visible from the southern hemisphere as detached patches of the Milky Way. These two irregular galaxies are close enough and massive enough that they are distorting our galaxy's outer gas disk, and the Milky Way's gravity is slowly pulling material from them in a great stream of gas that arcs across the sky. Andromeda has its own system of dwarf satellites, many of them arrayed in a strange, flat plane that is not well understood. In total, the local group is home to around 80 known galaxies, with the count still growing as deeper surveys reveal ever fainter members. But most of those galaxies are dwarfs, small, faint, irregular systems that would barely register next to a galaxy like the Milky Way. The mass of the local group is dominated by its two giants, and it will be those giants that ultimately determine the group's fate. The local group also illustrates a key feature of how galaxies are distributed everywhere in the universe. They cluster hierarchically. The Milky Way has satellite dwarf galaxies. The Milky Way and Andromeda, along with their satellites, belong to the local group. The local group belongs to the Virgo supercluster. The Virgo supercluster belongs to Laniakea. And Laniakea is one thread in the cosmic web. At each level of this hierarchy, gravity has organized matter on progressively larger scales, building up from individual stars to structures hundreds of millions of light years across through the same fundamental mechanism. Mass attracts mass, and over enough time, the initial clumping becomes more and more extreme. Galaxy shapes and what they tell us. Before we travel further, we should pause to understand what we are traveling past, because not all galaxies are alike, and the shapes we encounter are not accidents. The form of a galaxy is a record of its history, evidence of how it formed, what it has consumed, how old its stars are, and what it has been through. Edwin Hubble, working in the 1920s, created the first systematic classification scheme for galaxy morphology, a diagram now known as the Hubble tuning fork. On one side sit elliptical galaxies, round to elongated blobs of mostly old red stars, with little gas or dust and almost no ongoing star formation. They range from nearly spherical to highly elongated, and they come in every size from tiny dwarf ellipticals containing only 1 million stars to the most massive galaxies known, which dwarf our entire Milky Way many times over. On the other side of the tuning fork are the spiral galaxies, of which the Milky Way and Andromeda are examples, rotating disks of stars, gas and dust, with spiral arms where young blue stars form and trace out the pattern. And between the two sits a hybrid class, lenticular galaxies, which have the disk of a spiral, but none of the arms, no gas, and little star formation, like a spiral that has run out of fuel. Irregular galaxies fall outside all of these categories. They have no obvious symmetry, no clear disk or ellipse. Many of them owe their chaotic forms to interactions with neighboring galaxies, close passes or ongoing mergers that have scrambled their structure. The Magellanic Clouds are irregulars. So are many of the most active star-forming galaxies in the universe, their gas violently compressed by collisions into bursts of stellar birth. What Hubble did not initially understand, and what took decades of follow-up to establish, is that these shapes are not a static taxonomy. They are stages in an ongoing process. Elliptical galaxies, which look old and dead, are often the product of spiral galaxies merging. When two spirals collide, the ordered rotation that creates disk structure is disrupted. Stars are flung into random orbits, and the result tends toward an elliptical form. The most massive ellipticals in the universe, sitting at the centers of rich galaxy clusters, have grown to their enormous size by cannibalizing smaller galaxies for billions of years, absorbing one after another until they became the dominant object in their cluster. In that sense, a giant elliptical is less a stable endpoint than a graveyard, the accumulated wreckage of dozens of galaxies that no longer exist separately. Spiral galaxies are relatively fragile by comparison. Their orderly disk structure requires ongoing gas accretion to sustain star formation, and the spiral pattern itself is actually a density wave, a rotating compression zone that triggers star formation as gas and dust pass through it, not a fixed structure of specific stars. The arms are not material features in the way the spokes of a wheel are fixed. They are patterns, like a wave in water. The water moves up and down, but the wave travels across the ocean independently. As a spiral galaxy ages, loses its gas supply, or is disturbed by gravitational interactions, the arms can fade. What remains may look more like a lenticular galaxy, a disk without arms, passively aging. Barred spirals, which include the Milky Way, have an additional feature: a straight bar of stars crossing the galactic center, with the arms emerging from the ends of the bar rather than from the nucleus itself. The bar forms through gravitational instabilities in the disk and appears to channel gas toward the galactic center, potentially feeding both star formation and the central supermassive black hole. More than half of spiral galaxies in the nearby universe are barred. In the early universe, bars were rarer, which tells us something about how galaxy disks stabilize and mature over cosmic time. Dwarf galaxies, those small, low-mass systems that make up the overwhelming majority of galaxies by number, occupy their own corner of this taxonomy. Dwarf ellipticals and dwarf spheroidals are the most common type of galaxy in the observable universe by count, even if they contribute relatively little to the total stellar mass. They are extraordinarily faint, and many were discovered only in recent decades when imaging surveys became sensitive enough to detect their diffuse stellar halos against the glow of the sky. The satellite galaxies of the Milky Way and Andromeda are mostly dwarf spheroidals, tiny, dark matter-dominated systems with only a few million to a few 100 million stars, barely more luminous than a single globular cluster in our own galaxy. They are, in a sense, the universe's most common product: small, ancient, mostly dark, contributing to the grand census, but doing almost nothing visible on their own. What all of this taxonomy points toward is the same conclusion. Galaxy morphology is not a rigid classification, but a record of process. The universe starts with gas and dark matter. Gravity does its work. Mergers happen, star formation proceeds, gas is consumed or stripped away, black holes grow. At the end of a few billion years, what you have depends on the initial conditions, the environment, and the specific history of interactions. And no two galaxies have had exactly the same history: the Virgo cluster and our cosmic neighborhood. Leaving the local group behind and traveling roughly 50 million light-years from Earth, we arrive at the nearest rich galaxy cluster, the Virgo cluster. This is a different order of structure than anything in the local group. Where the local group contains around 80 known galaxies dominated by two large spirals, the Virgo cluster contains more than 1,300 confirmed members, with the count likely to grow as surveys improve. It is the gravitational anchor of the larger Virgo supercluster, and it exerts a subtle pull on the local group itself, not enough to pull us in, given our outward trajectory, but detectable in the peculiar motion of our galaxy. At the heart of the Virgo cluster sits Messier 87, one of the most famous and well-studied galaxies in the sky. M87 is a giant elliptical galaxy, the largest and most massive member of the cluster, an object that represents what happens when a galaxy sits at the bottom of a gravitational well for billions of years, gathering mass from everything that falls toward it. It contains somewhere between 2 and 3 trillion stars, making it more than twice as massive as the Milky Way, and its outer halo extends nearly 200,000 light-years from its center. At the center of M87 sits a supermassive black hole with a mass of around 6.5 billion solar masses. It is the first black hole ever to be directly imaged, that famous orange ring released by the Event Horizon Telescope collaboration in 2019. M87 also produces one of the most spectacular jets in the local universe, a narrow beam of plasma and high-energy particles launched from the vicinity of the central black hole at nearly the speed of light, extending thousands of light years into intergalactic space. This jet was first photographed by Heber Curtis in 1918, though its nature was not understood for decades. It is powered by the extraction of rotational energy from matter spiraling into the black hole, and it is bright enough in radio wavelengths to have been one of the first powerful extragalactic radio sources detected by early radio astronomers. Surrounding M87 in the Virgo cluster are hundreds of other galaxies of all types and sizes: spirals, ellipticals, lenticulars, and irregulars, each with its own history and its own position in the cluster hierarchy. Galaxy clusters like Virgo are not merely collections of galaxies. They are also filled with a diffuse, extremely hot gas that has been heated by gravitational compression to temperatures of tens of millions of degrees. This gas outweighs all the stars in the cluster's galaxies combined, and it glows in X-rays, making galaxy clusters bright targets for X-ray observatories. The gas has been there for billions of years, trapping metals shed by the cluster's galaxies over cosmic time. The Virgo cluster itself is part of the Virgo supercluster, a structure spanning roughly 110 million light-years that contains the local group as one of its outlying members. But in 2014, a team led by astronomer Brent Tully of the University of Hawaii produced a new map that revealed the Virgo supercluster to be just a tributary of something far larger. By tracing the velocities of galaxies across hundreds of millions of light-years and identifying which galaxies were gravitationally flowing toward which central attractors, Tully's team defined a supercluster they named Laniakea, from the Hawaiian for immeasurable heaven. Laniakea and the Great Attractor. Laniakea is our true home supercluster, and its scale forces a recalibration of everything else in the journey so far. It spans roughly 520 million light-years in diameter and contains approximately 100,000 large galaxies. The Virgo cluster, our entire local group, the Milky Way, every galaxy we can see from Earth with the naked eye, all of it fits inside Laniakea, and all of it is oriented, in its large-scale motion, toward a central gravitational focal point called the Great Attractor. The Great Attractor is one of the stranger objects in the nearby universe, not because of what it is, but because of where it is. It sits in the direction of the constellation Norma, behind the dense dust and star fields of the Milky Way's galactic plane, the zone of avoidance, as astronomers call it, where our own galaxy blocks our view of everything beyond it. For much of the 20th century, astronomers could see that galaxies were moving towards something massive in that direction, but they could not see what it was. The peculiar velocities of galaxies over a region hundreds of millions of light-years across, all pointed toward this hidden object, including the local group, which is falling toward the Great Attractor at roughly 600 kilometers per second. When infrared and radio observations eventually penetrated the zone of avoidance, the Great Attractor was revealed to be centered on the Norma cluster, a dense cluster of hundreds of galaxies located about 150 to 250 million light-years from us. But the Norma cluster alone is not massive enough to explain all the motion. The Great Attractor is itself being pulled toward an even larger concentration, the Shapley supercluster, some 650 million light-years away, which is one of the largest concentrations of mass in the nearby universe. So Laniakea is not a closed gravitational system. It is being drawn outward as a whole. This is important to understand. Laniakea is not gravitationally bound. The member galaxies, clusters, and groups of Laniakea are not orbiting a common center, the way stars orbit the galactic center. They are flowing toward it, yes, but the universe's expansion and the acceleration of that expansion, driven by dark energy, mean that most of Laniakea will eventually be pulled apart. The Virgo cluster will not attract the local group. The local group will not merge with the Virgo cluster. Our future is to drift away as the space between us and all distant structures expands faster than gravity can compensate. In the far future, billions of years from now, even our nearest neighboring galaxy groups will be beyond reach. What Laniakea represents, then, is not a permanent structure, but a snapshot, the current arrangement of matter in our cosmic neighborhood, the shapes that gravity has had 13.8 billion years to carve out. And it is just one node in a vastly larger pattern. The cosmic web. Pulling back far enough to see Laniakea from outside, moving our imaginary viewpoint to a distance where 520 million light-years becomes a modest dot on the map, we encounter something that looks almost biological. The universe's matter is not distributed in random clumps. It is organized into an intricate network of filaments, sheets, and nodes separated by enormous empty regions. This is the cosmic web, and it is the largest coherent structure that exists. Filaments are the threads of the web, elongated, roughly cylindrical concentrations of dark matter and gas, along which galaxies are strung like beads. A prominent filament can stretch several 100 million light-years from end to end, though they are incredibly diffuse, more like tenuous rivers of matter than anything solid. Where two or more filaments intersect, they form nodes, the densest regions in the universe, where matter has accumulated over billions of years into massive galaxy clusters. Between the filaments, and bounded by the sheets that connect them, lie the voids. Vast regions of pure emptiness that contain far fewer galaxies than expected. Voids are typically 30 to 300 million light-years in diameter, and together they occupy the overwhelming majority of the universe's volume. Most of the universe is, by volume, essentially empty. The web was not designed. It grew. It emerged from tiny density variations in the very early universe, quantum fluctuations in the energy of space itself, imprinted during the first fraction of a second after the Big Bang, and amplified as the universe expanded. Where the density of matter was slightly higher than average, gravity pulled in more material over time, further increasing the density. Where the density was slightly below average, material drained away toward the denser regions, leaving the underdense zones emptier. Over billions of years, this process, gravitational collapse on cosmological scales, produced the web we see today. Dark matter was essential to this process. Ordinary matter, the atoms and molecules that make up stars and planets and human beings, cannot collapse easily on its own in the early universe because radiation pressure keeps pushing it around. Dark matter, which does not interact with light and therefore does not feel that radiation pressure, can collapse much more readily. The web's fundamental skeleton is made of dark matter, invisible halos and filaments that formed first, providing the gravitational scaffolding into which ordinary matter later fell. The galaxies we see are luminous traces of an underlying dark matter structure that we cannot observe directly, but whose presence is inferred from the arrangement of everything visible. Some structures within the cosmic web have been given names that reflect their scale. The Sloan Great Wall is a sheet of galaxies roughly 1.37 billion light-years long, identified in data from the Sloan Digital Sky Survey in 2003, and at the time considered the largest known structure in the observable universe. The South Pole Wall, discovered in 2020 by Brent Tully's team as they extended their mapping effort, is a similarly massive structure lying just beyond Laniakea. wrapping around its southern edge in a great arc spanning more than 200 degrees of sky and reaching some 500 million light-years in depth. The Hercules Corona Borealis Great Wall, estimated at over 10 billion light-years in extent, the largest single structure yet identified, pushes against theoretical expectations for how large a coherent structure the universe can produce in the time available. There is a theoretical ceiling on how large a coherent structure can grow. At scales beyond roughly 300 to 400 million light-years, the universe appears statistically homogeneous, meaning that if you average the density of matter over large enough volumes, it becomes roughly the same everywhere. This is a prediction of the standard cosmological model, and most observations support it. But structures like the Hercules Corona Borealis Great Wall, if confirmed as truly coherent objects, seem to push against that expectation, and their existence is one of several open questions about how large a structure cosmic time and physics can actually produce. Galaxy clusters, the densest nodes. Traveling through the web, we keep arriving at its densest points. Galaxy clusters. These are the largest gravitationally bound structures in the universe. Collections of hundreds to thousands of galaxies, vast quantities of hot gas, and enormous amounts of dark matter, all held together in a common gravitational potential. Understanding them is essential to understanding the cosmic journey, because they are the places where galaxy evolution takes its most dramatic turns. The Coma Cluster, roughly 320 million light-years from Earth, contains more than 1,000 galaxies and is one of the best-studied rich clusters in the sky. It was observations of the Coma Cluster in the 1930s that first led astronomer Fritz Zwicky to propose the existence of dark matter. Zwicky measured the velocities of galaxies within the cluster and found that they were moving far too fast to be explained by the visible mass of the cluster alone. The galaxies should have escaped, should have flown apart billions of years ago, if the only gravity holding them was coming from the stars and gas he could see. There had to be additional mass, invisible, holding the cluster together. It took another half-century for this idea to gain widespread acceptance. But the Coma Cluster was where the first solid evidence appeared. Most of the galaxies in rich clusters like Coma are ellipticals and lenticulars, old, red, gas-poor systems that have long since stopped forming stars. This is not a coincidence. The cluster environment is hostile to star formation in several ways. The dense intracluster gas, heated to tens of millions of degrees by gravitational compression, can strip the cooler gas from infalling galaxies in a process called RAM pressure stripping. Like a headwind that blows the interstellar material out of a galaxy as it plunges into the cluster. Once a galaxy loses its gas, it loses its ability to form new stars, and it gradually reddens as its remaining stellar population ages. Gravitational harassment, such as repeated close encounters with other cluster galaxies that distort and heat the disk, further disrupts any order that might remain. Clusters are, in this sense, graveyards for spirals. They transform active, star-forming galaxies into passive, aging ellipticals over timescales of billions of years. The most extreme galaxy clusters are almost staggeringly large. The Bullet Cluster, roughly 3.7 billion light-years away, became famous in 2006 when observations of it provided the most direct evidence to date for dark matter's existence. The Bullet Cluster consists of two galaxy clusters that have passed through each other. The visible gas of the two clusters collided, slowed, and heated, producing a bow shock visible in X-rays. But the dark matter halos of the two clusters, mapped by gravitational lensing of background objects, sailed through each other unimpeded, separating from the gas and revealing themselves as the dominant mass component. The separation of the X-ray gas from the gravitational lensing mass was direct, geometric evidence that most of the cluster's mass is in a non-interacting dark component. El Gordo, or ACT-CLJ 0102-4915, is one of the most massive galaxy clusters known, located about 7 billion light-years from Earth. Its mass is roughly 2,000 trillion solar masses, roughly 2,000 times the mass of the Milky Way. It too appears to be a merger of two massive clusters, and the energy involved in such a collision staggers the imagination. Two of the largest gravitationally bound objects in the universe, each containing hundreds of galaxies, slamming into each other at millions of kilometers per hour. The voids between. Between every cluster and every filament, making up the vast majority of the universe's volume, lie the voids. We should not pass through them quickly in our journey, because they are not nothing. They are one of the most important structural features of the universe. Cosmic voids are not perfectly empty. They contain scattered, isolated galaxies, some of them surprisingly large, and thin wisps of diffuse gas. But their density is far below the cosmic average, and the galaxies within them are affected by their isolation in ways that differ subtly from galaxies in filaments or clusters. Void galaxies tend to be bluer, less massive, and more actively forming stars than their counterparts in denser environments. They have fewer neighbors to interact with, less cold gas stripped from them by cluster winds, and more of their original interstellar material intact. In a sense, void galaxies are the universe in a more pristine state, less processed by the violent history of clusters and mergers. The largest void within the relatively nearby universe is the Boötes void, discovered in 1981 by Robert Kirshner and his collaborators. The Boötes void is roughly 330 million light-years in diameter and contains far fewer galaxies than would be expected given the volume. About 60 have been identified inside it, where several thousand might be expected. Its sheer size attracted speculation when it was first discovered, because it seemed large enough to be difficult to explain through the standard mechanisms of void formation. Further studies showed that the Boötes void is actually the result of several smaller voids that have merged over cosmic time, creating a larger underdense region. As matter was gravitationally evacuated toward the surrounding walls and filaments, voids expand. As the universe ages, the underdense regions grow larger and emptier, and the dense structures they are bound by become more concentrated. In the far future, dark energy's acceleration of the universe's expansion will make this process more extreme. Voids will grow into vast deserts of space as the matter they once contained continues to cluster elsewhere. There is a real sense in which the cosmic web is not a stable architecture, but a dynamic process, still in the act of being sculpted, with the final result billions of years from completion. The dipole repeller, identified in 2017, adds another dimension to this picture. For decades, astronomers trying to explain the motion of the local group focused on the Great Attractor as the dominant gravitational influence. But a team led by Yehuda Hoffman of the Hebrew University found that the picture was incomplete. There was not only a pull toward the Great Attractor, but also a push away from a massive void in the opposite direction. This void is a region so underdense that its lack of gravitational pull contributes to the local group's motion, just as significantly as the Great Attractor's excess pull. We are not only being attracted toward denser regions, we are also being repelled from emptiness, a push equally real as any pull. What voids also reveal is that the universe is not merely a collection of objects, but a collection of relationships. A galaxy's properties are shaped not just by what it contains, but by what surrounds it. A spiral galaxy, sitting alone in the middle of a void, has a fundamentally different evolutionary history than an identical spiral, sitting in the outskirts of a rich cluster. Different merger rate, different gas accretion history, different ram pressure history, different exposure to tidal harassment. The environment writes itself into the galaxy's stars and gas, encoding a history of where the galaxy has been in the cosmic web. When astronomers look at a galaxy's color, its star formation rate, the degree to which its disk is disturbed, the fraction of its gas that has survived, they are, in part, reading a biography written by large-scale structure. The void galaxies we pass through on this journey are in some ways the most original galaxies in the universe, the least processed, the least altered, the closest to what a galaxy looks like when it is left largely alone to evolve according to its own internal physics. A census of what's out there. Stepping back from individual structures and looking at the universe as a whole, the most natural question becomes, how many galaxies are there? The answer has changed dramatically over the past century, and it continues to evolve. For most of the 20th century, estimates placed the total number of galaxies in the observable universe at around 100 billion. The observable universe is roughly 93 billion light-years in diameter, and 100 billion seemed like an astronomically large number already. Then, in 2016, a study led by Christopher Consolis at the University of Nottingham used data from multiple ground and space telescopes combined with theoretical models of galaxy formation to produce a new estimate. Roughly 2 trillion galaxies, 10 times more than previously thought. The revision came from accounting for the vast numbers of small, faint galaxies at high redshift that were too dim and distant for earlier telescopes to see, but that must have existed based on our understanding of how structure forms. That 2 trillion figure itself may require revision. A 2021 study using the camera aboard the New Horizons spacecraft, which has travelled far enough from the inner solar system to escape the zodiacal light pollution that affects Earth-based measurements, found that the total amount of visible light in deep sky patches was consistent with a smaller number of galaxies, several hundred billion rather than trillions. The discrepancy is still being worked through. What is agreed upon is that the true census requires defining what counts as a galaxy, because the objects in question range from dwarf systems containing only 1 million stars to giants containing trillions. The definition matters enormously for the total count. What astronomers can say with confidence is that most of the galaxies in the universe are not like the Milky Way. Most are small, most are dwarfs, compact systems with masses far below our own galaxy. And many are so faint that they have no official designation, known only as statistical contributions to deep field surveys. The bright photogenic spirals and ellipticals that dominate astronomical images represent only a small fraction of the total galaxy population. The typical galaxy, if there is such a thing, is small, old, and largely invisible to everything but the most sensitive instruments. The total count also changes over time. Galaxies merge. The universe today contains fewer but larger galaxies than the universe of 5 billion years ago, which contained fewer but larger galaxies than the universe of 10 billion years ago. Galaxy formation was most vigorous in the first few billion years of cosmic history, when the universe was denser and gas supplies were fresh. As gas has been consumed, as mergers have combined smaller galaxies into larger ones, and as the expansion of the universe has made it harder for widely separated galaxies to fall together, the rate of new galaxy formation has slowed. The universe is, in some sense, winding down from its most creative period. The peak of cosmic star formation, the moment in the universe's history when the most new stars were being born, per unit of time across the entire observable volume, occurred roughly 10 billion years ago, when the universe was about 4 billion years old. Astronomers call this the cosmic noon, and the galaxies of that era were, on average, far more active than what we see in the nearby universe. They were forming stars at rates tens or even hundreds of times higher than a typical galaxy forms them today. The star-forming galaxies of cosmic noon were also more irregular, less orderly than the spirals and ellipticals that dominate the nearby universe, their morphologies disturbed by the higher rate of mergers and interactions in the denser, younger cosmos. JWST is allowing astronomers to study galaxies from and near cosmic noon in extraordinary detail for the first time, revealing the internal structure of these ancient active systems and tracing how their gas was being consumed, redistributed, and eventually exhausted. The nearby universe we see today is, in a real sense, the quiet aftermath of an earlier age of much greater activity. What we see when we look back in time. Here is one of the most profound features of this journey. When we look outward in space, we are simultaneously looking backward in time. Light travels at a finite speed, approximately 300,000 kilometers per second. And because the universe is so vast, the light from distant galaxies was emitted long ago. The light reaching our telescopes from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. The galaxy we see is not the galaxy as it exists now. It is the galaxy as it was a billion years in the past. This means that a journey through space is also a journey through cosmic history. The nearby galaxies we see, the local group, the Virgo cluster, the structures within Laniakea, are galaxies in their current mature state, more than 13 billion years after the Big Bang. As we travel outward and look at more distant galaxies, we are seeing galaxies as they appeared at progressively earlier epochs. The most distant galaxies visible to current telescopes are being observed as they existed when the universe was only a few 100 million years old, when everything was denser, hotter, more chaotic, and more energetic than today. The James Webb Space Telescope, launched in December 2021 and operating since mid-2022, was built specifically to see these early galaxies. Its 6.5-meter mirror and extreme infrared sensitivity make it capable of detecting light that has been stretched by the expansion of the universe from ultraviolet into infrared wavelengths over billions of years of travel. The universe's expansion stretches light. The farther away a source is, the more the expansion has stretched its light during transit, shifting it toward redder and eventually infrared wavelengths. Redshift is astronomers' measure of distance and look-back time. A galaxy with a redshift of 2 is being seen as it appeared when the universe was roughly 3 billion years old, while a galaxy with a redshift of 10 is being seen from when the universe was only about 500 million years old. Before JWST, the most distant confirmed galaxy had a redshift of around 11, corresponding to the universe at roughly 400 million years of age. JWST demolished that boundary almost immediately upon beginning scientific operations. The JWST Advanced Deep Extragalactic Survey found hundreds of galaxies from the first 650 million years of cosmic history. Then, in early 2024, a galaxy known as J ADS-GS-114-0 was confirmed at a redshift of 14.18, corresponding to the universe at only about 300 million years of age. This galaxy was not only distant, but unexpectedly bright and large, over 1,600 light-years across, producing its light almost entirely from young stars rather than from a central black hole. The oxygen detected in its spectrum indicated that multiple generations of massive stars had already lived and died within it, which was astonishing given how little time had elapsed since the Big Bang. Then, in early 2025, JWST broke its own record. A galaxy named MOM-Z114, confirmed in a study published in January 2026, was established at a redshift of 14.44, placing it at just 280 million years after the Big Bang. What makes MOM-14 remarkable beyond its distance is that it was not expected to exist. At this stage in the universe's history, theoretical models had not predicted bright, substantial galaxies to be present in any numbers. JWST has now found more than 100 relatively bright galaxies from this era, where almost none were expected, a systematic discrepancy between prediction and observation that suggests the standard models of early galaxy formation are missing something important. The first galaxies and cosmic dawn. At the farthest reaches of our journey, we are approaching an era in cosmic history known as cosmic dawn, the period when the first light sources switched on in the universe after the darkness of the primordial hydrogen cloud. Understanding this era is one of the central goals of 21st century astronomy. After the Big Bang, for the first roughly 380,000 years, the universe was a hot, dense plasma of protons, neutrons, and electrons, so thoroughly mixed that light could not travel freely. It was constantly scattered. Then, the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms, and suddenly the universe became transparent. Light was free to travel. That moment is what we observe as the cosmic microwave background, the oldest light in the universe, a faint glow of microwave radiation coming from all directions, bearing the imprints of the tiny density variations that would eventually grow into the cosmic web. After that transition, the universe entered what cosmologists call the Dark Ages, a period lasting perhaps 200 to 400 million years, during which no light sources existed, no stars, no galaxies, just hydrogen and helium gas, slowly being drawn together by gravity into the dark matter halos that had been forming since the Big Bang. When the first clumps of gas grew dense enough and hot enough at their centers, the first stars ignited, and the Dark Ages ended. Those first stars were almost certainly nothing like the stars we see today. Composed purely of hydrogen and helium, the only elements that existed before stars forged heavier elements in their interiors, they were likely enormously massive, perhaps 100 to 1,000 times the mass of the Sun. Such massive stars burn ferociously bright and die young, often in spectacular explosions. They produced the first heavy elements and the first intense ultraviolet radiation, which began ionizing the neutral hydrogen gas that filled the universe, gradually transforming the cosmos from a fog of neutral gas into the clear, ionized medium we observe today. This transformation, called the epoch of rionization, took place roughly between 400 million and 1 billion years after the Big Bang. The galaxies JWST is finding from 280 to 500 million years after the Big Bang are some of the earliest contributors to this reionization. Some of them are unexpectedly bright and already surprisingly large, implying that galaxy formation in the early universe was more rapid and efficient than models predicted. One galaxy, JADES-GS-Z13-1, observed at 330 million years after the Big Bang, showed a type of hydrogen emission that should have been impossible at that epoch. The surrounding neutral hydrogen gas should have blocked it. The detection suggests that the galaxy had already created a bubble of ionized space around itself, punching a hole through the fog of the Dark Ages, though exactly how it managed this remains an open question. The Cosmos Web Survey, released publicly in June 2025, provided the largest map of the universe ever assembled from JWST data, a catalogue of nearly 800,000 galaxies spanning nearly all of cosmic time. This catalogue found roughly 10 times more galaxies in the earliest epochs than predicted, and discovered supermassive black holes at early times that were invisible even to Hubble. The gap between what the standard cosmological model predicts for the early universe and what is actually observed may prove to be one of the most significant unresolved problems in modern cosmology. A sign that either galaxy formation was far more efficient than understood, or that the universe's early history involved processes that models do not yet capture. One specific possibility being explored is that the initial mass function of stars, the distribution of masses at which stars form, was different in the early universe than it is today. If the first generations of stars were systematically more massive than stars forming today, they would produce more light per unit of gas consumed, making early galaxies brighter than expected, even if they contain the same amount of stellar mass. Another possibility involves dust. If early galaxies had less dust than models assume, more of their light would escape unabsorbed, making them appear brighter. A third possibility is more radical, that the nature of dark matter itself, or the specific dynamics of inflation that seeded the density variations driving structure formation, differs from the simplest assumptions in ways that allow more rapid galaxy formation. Theorists are actively working through all of these paths, and the answer may require more than one of them. What is certain is that JWST has changed the picture of the early universe more profoundly than almost anyone anticipated before launch. The telescope was expected to find distant galaxies. It was not expected to find so many of them, so bright, so early. Every new observation from the deep fields has added to a body of evidence that the universe was not as quiet or as dark in its first few 100 million years as the standard model suggested. Something was happening quickly, efficiently, and with more energy output than predicted. And whatever that something was, it shaped everything that came after. Active galaxies and the black holes that power them. Throughout our journey, we have been passing galaxies in all their diversity, but some galaxies are not quiet at all. Their centers blaze with energy so intense that they outshine everything else in the galaxy combined, sometimes by factors of thousands. These are active galactic nuclei, and understanding them changes the picture of how galaxies live and die. At the heart of every massive galaxy is a supermassive black hole. In most galaxies, including our own Milky Way, that black hole is mostly dormant, fed so little material that it produces almost no detectable output. But when material falls toward the black hole in significant quantities, whether from gas clouds spiraling in along filaments, from gas disturbed by a galaxy merger, or from material tidally disrupted as stars pass too close, the infalling matter forms an accretion disk, heats to extreme temperatures, and radiates prodigiously. The energy released by matter falling toward a supermassive black hole can exceed the combined light output of the entire galaxy's stellar population by orders of magnitude. Quasars are the most extreme version of this phenomenon. They are the most luminous, sustained light sources in the universe, and they were far more common in the past. The quasar era peaked roughly 10 billion years ago, when galaxies were younger, denser, and more frequently merging. Looking back toward high redshift, quasars light up the early universe like beacons, making them detectable at distances where ordinary galaxies are too faint to see. The most distant quasars, at redshifts above 7, are being observed when the universe was less than 1 billion years old, and their central black holes, some already weighing hundreds of millions to billions of solar masses, present a significant challenge to formation models. How do black holes that massive form so quickly in a universe that is only 1 billion years old? What these active phases mean for galaxy evolution is one of the most actively debated topics in astrophysics. There is good evidence that the energy output of active galactic nuclei can regulate star formation. The outflows and jets of an active nucleus can heat and expel gas from a galaxy, cutting off the supply of cold gas needed to form new stars. This process, called AGN feedback, may be responsible for shutting down star formation in massive elliptical galaxies and quenching their evolution into passive, aging systems. The supermassive black hole at the center of a galaxy is not merely a passenger in the galaxy's history. It may be one of the drivers of it, and the tight correlation between a galaxy's black hole mass and the mass of its central stellar bulge, observed across thousands of galaxies, is a striking fingerprint of this co-evolution, though the causal mechanism is still being worked out. Radio galaxies add a further dimension to this. When the jets from an active nucleus extend far beyond the galaxy itself, sometimes reaching millions of light years into the surrounding intracluster medium, they deposit enormous amounts of energy into the hot gas surrounding the galaxy. This energy can offset the cooling of the intracluster gas that would otherwise rain back down onto the galaxy and fuel new star formation. In giant ellipticals at the centers of clusters, this jet-driven heating appears to be the dominant mechanism preventing the enormous cooling flows of hot gas from reigniting star formation on a massive scale. Without this feedback, some of the most massive galaxies in the universe would look very different from what they are: active, star-forming spirals, rather than the passive, aging ellipticals we actually observe. The black hole and the galaxy are locked in a long-running conversation, and the black hole frequently has the louder voice. Galaxy mergers and the violence of gravity. As we travel through the universe, we encounter mergers everywhere, not quick collisions like highway accidents, but slow, gravity-driven dances lasting hundreds of millions of years. Galaxy mergers are the central mechanism by which large galaxies grow, and the evidence for them is written across the sky in the form of distorted tails, bridges of stars, and chaotic systems that no longer have any clear shape. When two galaxies approach each other, gravity does not allow a clean miss. Tidal forces begin to distort both systems, pulling out stars and gas in long streamers called tidal tails, sometimes stretching millions of light years. The first encounter may not immediately merge the two galaxies. They may pass through each other, separate, and then fall back together, oscillating for billions of years before the cores finally coalesce. During each passage, the gas in the galaxies is compressed by tidal forces and gravitational shocks, triggering bursts of star formation so intense that the combined system can briefly outshine everything else in its vicinity. These star-bursting mergers are the origin of some of the brightest infrared galaxies in the universe. The antennae galaxies, named for the long tidal tails that resemble insect antennae, are one of the closest and best observed mergers in the sky. A pair of spirals about 45 million light-years away that began interacting roughly 600 million years ago. JWST's observations of the antennae have revealed details of the star formation occurring in the overlap region that were invisible to earlier telescopes. Hundreds of young star clusters embedded in their birth clouds. Evidence that mergers can be extraordinarily productive nurseries for new stellar generations, even as they disrupt the structure of the parent galaxies. The Cartwheel Galaxy, roughly 500 million light-years from Earth, is a ring galaxy. The spectacular result of a smaller galaxy having plunged almost directly through the center of a larger spiral galaxy. The impact sent an outward rippling density wave through the disk, like a stone dropped in still water, compressing gas into a ring of intense star formation that now glows with young blue stars. Inside the ring, the original disk structure has been almost entirely disrupted. The culprit galaxy has escaped and now sits nearby, distinguishable only because its orbit can be traced backward. JWST imaged the cartwheel in extraordinary detail in 2022, revealing the structure of the star formation ring and the complex dust lanes in unprecedented clarity. At the centers of rich galaxy clusters, the most extreme mergers occur quietly and persistently over billions of years. The brightest cluster galaxies, those enormous ellipticals sitting at the gravitational bottom of their cluster, grow by accreting infalling galaxies through a process called dynamical friction, which bleeds orbital energy from a smaller galaxy as it spirals inward. The smaller galaxy is gradually dismembered, its stars added to the outer halo of the central giant, its core occasionally surviving as a compact satellite for billions of years before it too is absorbed. The most massive galaxies in the universe owe their size entirely to this repeated cannibalism, making their vast halos essentially the accumulated ghosts of galaxies that no longer exist. The universe's missing baryons and what fills the space between. Something important has been left out of this journey so far, and it lives in the spaces between galaxies. When astronomers take stock of all the ordinary matter in the universe, all the protons and neutrons, all the atoms, all the stuff that makes up stars and gas clouds and planets and people, they find that roughly half of it cannot be accounted for by what is visible. The stars and galaxies visible to telescopes contain only about half the total ordinary matter that cosmological models and observations of the early universe predict should exist. The answer, supported by increasing observational evidence, is that most of the universe's ordinary matter is not in galaxies at all. It is spread in an extremely diffuse, extremely hot gas called the warm-hot intergalactic medium, or WIM, that fills the filaments of the cosmic web. This gas, heated to temperatures between 100,000 and 10 million degrees by gravitational compression and shocks as matter fell into the web's structure, is so thin that it glows only faintly in soft X-rays and ultraviolet light, faint enough to have been largely invisible to earlier generations of telescopes. Direct detection of the WIM has been one of the most sought-after goals in observational cosmology for 2 decades. Evidence for it has accumulated through absorption features in the spectra of distant quasars. When the tenuous web gas lies between a quasar and Earth, it absorbs specific wavelengths of the quasar's light in patterns that reveal the temperature, density, and composition of the gas. In 2019, a team from the Riken Institute in Japan and Durham University in the UK published the first direct imaging of a cosmic web filament in emission, light actually radiating from the gas connecting two galaxy clusters, illuminated by the combined ultraviolet output of star-forming galaxies acting as flashlights. The image was not spectacular to look at, but it was one of the most significant observational confirmations of the Webb's gaseous skeleton in astronomical history. Understanding the warm-hot intergalactic medium matters because it closes the baryon budget. It accounts for the matter that is theoretically present but was observationally missing. It also matters because this gas is the reservoir from which galaxies have drawn material throughout their lives. Cold gas flows from the cosmic web into galaxies along filaments, fueling the star formation that produces the stars and planets and every heavy element in the universe. The web is not a static backdrop to galaxy evolution. It is the supply chain that has fed every galaxy we have passed on this journey, from the first tiny systems near the dawn of cosmic time to the enormous clusters we see today. The observable horizon and what lies beyond. At the far edge of our journey, we arrive at a limit that has nothing to do with distance and everything to do with time. The observable universe has a horizon. Light travels at a finite speed, and the universe has a finite age. No signal, no matter how fast, can have reached us from a distance so great that the time required for light to cross it exceeds the age of the universe itself. This gives us a sphere, the observable universe, beyond which, no matter what instruments we build, we cannot see. Not because nothing is there, but because the information from there has not had time to reach us. The cosmic microwave background, the faint afterglow of the Big Bang that permeates the sky in all directions, marks the edge of this sphere. It represents the moment, about 380,000 years after the Big Bang, when the universe first became transparent and light was free to travel. We can see no further back in time because there was no freely traveling light before that moment. The CMB comes from a surface about 46 billion light-years away from us in every direction, farther than the 13.8 billion light-years that corresponds to the age of the universe, because the universe has been expanding during the time that light was traveling. The total universe, the universe beyond our observable horizon, is certainly larger than what we can see. The Planck satellite's measurements of the CMB's geometry suggest that the universe is spatially flat or very close to it, which is consistent with it being vastly larger than the observable portion. How much larger is genuinely unknown. Whatever is out there is, in the most literal sense, beyond reach. Not a matter of technological limitation, but a fundamental constraint, written into the physics of light and the age of time itself. Some versions of inflationary cosmology suggest the existence of an eternal inflation producing a multiverse of bubble universes, each potentially with its own physical constants, of which ours is one. These ideas remain in the domain of theoretical speculation, well beyond what observation can currently test. But they are the natural extensions of what we do know, that our observable universe is not the universe in total, but a patch of something larger, perhaps vastly larger, perhaps without any limit at all. How we mapped it all. This journey, from the Milky Way to the edge of the observable universe, was not mapped all at once. It was assembled over decades of observation using instruments and techniques that progressively extended humanity's reach. For most of human history, the universe was the Milky Way. The existence of other galaxies was not demonstrated until 1923, when Edwin Hubble used Cepheid variable stars to measure the distance to what was then called the Andromeda Nebula, and establish that it lay far beyond the boundaries of the Milky Way. It was a discovery that instantly expanded the known universe by a factor of many thousands. Hubble's subsequent work established that almost all distant galaxies are moving away from us, and that their recession speeds are proportional to their distances. The relationship now known as Hubble's law, which was the first evidence that the universe is expanding. The Great Galaxy Redshift surveys of the late 20th and early 21st centuries transformed the two-dimensional picture of galaxies scattered across the sky into three-dimensional maps of the cosmic web. The CFA Redshift survey of the late 1970s and 1980s was the first systematic effort, and it produced the first clear evidence of large-scale structure. Walls and voids in the galaxy distribution that contradicted the assumption of smooth uniformity. The two DF Galaxy Redshift Survey and the Sloan Digital Sky Survey extended this mapping to cover hundreds of thousands and then millions of galaxies, revealing the web in its full complexity over regions of several billion light-years. The Euclid Space Telescope, launched in 2023, is extending these surveys to even greater distances and precision, with the goal of mapping the large-scale structure of the universe well enough to constrain the properties of dark energy and test whether it has varied over cosmic time. The development of radio astronomy added an entirely new dimension to the picture. Radio galaxies, quasars, pulsars, and the cosmic microwave background were all discovered through radio observations and transformed cosmology. X-ray astronomy revealed the hot gas-filling galaxy clusters. Infrared astronomy penetrated the dust that hides the densest star-forming regions. Gravitational wave detection, beginning with the first direct detection by LIGO in 2015, opened a completely new observational window that does not use light at all. It reads the universe in the vibrations of space-time itself, detecting events like merging black holes and neutron stars that were previously completely invisible. Each new wavelength range and each new type of signal has added detail and complexity to the map. JWST represents the current frontier. Its findings have already complicated the standard model of galaxy formation in ways that will take years to fully understand. The Nancy Grace Roman Space Telescope, scheduled to launch in 2026 or 2027, will survey vastly larger areas of the sky in infrared wavelengths, finding thousands of high redshift galaxies and extending the cosmic census across time. The Vera C. Rubin Observatory, now entering full operations, will survey the sky repeatedly and deeply in optical wavelengths, mapping billions of galaxies and tracking how the large-scale structure of the universe evolves. The extremely large telescope, under construction in Chile with a mirror 39 meters across, will obtain detailed spectra of individual galaxies seen by JWST and Roman, probing their chemistry, star formation history, and dynamics in ways that current instruments cannot reach. The map is still being drawn. There is something philosophically interesting about the relationship between the tools and the knowledge they produce. Each instrument does not merely extend the previous one's reach. It also reveals that the universe is different from what the previous instrument suggested. Every time humanity has built a significantly more powerful eye, the universe has revealed a layer of itself that was previously hidden, and that hidden layer has always turned out to be important. There is no reason to think this pattern has ended. The universe has been consistently more complex, more layered, and more surprising than expected at every stage of the investigation. The appropriate response to that history is not confidence that we are nearly done, but anticipation that the next instrument will again show something unexpected. What this journey reveals about scales. Flying through every galaxy in the observable universe forces a confrontation with scales that resist intuition. We are comfortable with numbers we can picture: $1 million, 1,000 miles, a few hundred years. The universe does not accommodate our scale preferences. The Milky Way is 100,000 light-years across. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, takes 100,000 years to cross our galaxy. The Andromeda Galaxy is 2.5 million light-years away. The Virgo cluster is 50 million light-years away. Laniakea is 520 million light-years across. The observable universe is 93 billion light-years in diameter. These numbers do not mean anything the way the number 10 means something. They are not computable in terms of human experience. They require a different relationship with magnitude. One thing this journey reveals is that the universe is simultaneously almost entirely empty and intricately patterned. The distance between galaxies is typically tens to hundreds of times larger than the galaxies themselves. The distance between stars within galaxies is millions of times larger than the stars. At every scale, the stuff of the universe is embedded in vast empty surroundings. And yet, matter is not randomly distributed. It is organized by gravity and thermodynamics and the quantum fluctuations of the early universe into structures of extraordinary intricacy. The cosmic web, spanning billions of light years, was laid down by physics operating at the quantum scale in the first fraction of a second of time. The largest and the smallest are connected. Another thing this journey reveals is that the universe has a history, and that history is visible. We are not looking at a static cosmos when we look at the night sky. We are looking at different eras, the nearby galaxies as they are today, more distant galaxies as they were millions and billions of years ago, the faintest detectable objects as they existed near the beginning of time. Every image from a powerful telescope is a time machine. The universe visible to our instruments is not a snapshot of a moment, but a composite of all moments since the first light was emitted, layered on top of each other. Reading the cosmos is reading history, a history that begins before there was anyone to read it, and may continue long after the last reader is gone. There is also something the journey reveals about contingency, about how different the universe could have been, and how narrow the conditions for what we observe actually are. The cosmic web's structure was seeded by quantum fluctuations that are, at their root, probabilistic. A slightly different realization of those fluctuations, in the first fraction of a second after the Big Bang, would have produced a different web, different galaxy distributions, different clusters, different histories of star formation. The particular arrangement of matter we inhabit, including the specific location of the Milky Way in a relatively quiet backwater of the Virgo supercluster, away from the violent centers of rich clusters, is one outcome among an enormous space of possible outcomes. Whether that particular arrangement had anything to do with the emergence of life on Earth, and whether life requires the relatively stable, suburban environment of a void-adjacent spiral galaxy rather than the turbulent core of a rich cluster, is a question that connects cosmology to biology in ways that are only beginning to be explored. What the scale confrontation ultimately produces, if followed honestly, is not despair but a recalibrated sense of what matters. The universe does not care about the scale of any particular event within it. Galaxies merge and die without ceremony. Stars explode. Clusters collide in slow motion over billions of years, unmourned and unwitnessed. Scale is not significance. The pale blue dot hanging in a sunbeam, 3.7 billion miles from home, is the most significant object we know of in the observable universe, not because of its size, but because of what it contains. The only confirmed example of matter understanding itself. What remains unknown? This journey is honest only if it acknowledges what is not known, because the unknown parts are large. Dark matter makes up roughly 27% of the universe's total energy density. It shapes everything: the cosmic web, galaxy formation, the rotation curves of galaxies, the bending of light by galaxy clusters. And yet, after nearly a century of accumulating evidence for its existence, we have no confirmed direct detection of a dark matter particle. Every candidate proposed by particle physics has so far failed to appear in detectors. The simplest hypothetical dark matter particles, weakly interacting massive particles, or WIMPs, have been searched for in deep underground detectors for decades without appearing. Alternative candidates, including axions and sterile neutrinos, remain similarly elusive. The nature of dark matter is the most important open question in physics and astronomy combined. Dark energy, responsible for the accelerating expansion of the universe, is even more mysterious. It makes up about 68% of the universe's total energy density and is currently described as a cosmological constant, a uniform energy density of space itself that drives expansion at an accelerating rate. Whether it truly is constant, or whether it varies over time and space, is one of the central questions that surveys like Euclid and Roman are designed to answer. Recent data from the DESY survey, which measured the positions of tens of millions of galaxies across cosmic time, produced hints that dark energy may not be constant, that it may vary in ways that deviate from the simplest model. These hints are not yet definitive, but they are being taken seriously, and if confirmed, they would require a fundamental revision of our cosmological picture. The tension in measurements of the Hubble constant, the rate of cosmic expansion, is another unresolved issue. Two independent methods of measuring this rate give values that disagree by about 8%, more than can be explained by measurement uncertainty alone. One method uses the CMB and early universe physics. The other uses galaxies and standard candles in the local universe. They should agree if the standard cosmological model is complete, and they do not. This Hubble tension has persisted and intensified over a decade of increasingly precise measurements, and it may indicate that some ingredient is missing from our understanding of how the universe has evolved. And then there is the question raised by JWST's early universe observations. Why are there so many bright galaxies so soon after the Big Bang? Whether the answer requires patching the existing model with adjustments to star formation efficiency and feedback, or whether something more fundamental about the physics of the early universe is missing, remains genuinely open. The universe has been forthcoming with evidence. It has not yet been forthcoming with explanations. The shape of everything. Before we return to where we started, one final question. What shape is all of this? The large-scale structure of the observable universe looks, when rendered in 3 dimensions by galaxy surveys, like a sponge or a foam. Dense walls and filaments surrounding large empty bubbles of void. But this foam has no preferred direction, no center, and no edge within the observable sphere. Observations of the CMB confirm that the universe looks statistically the same in every direction from our location. Whatever structure exists, it is not organized around any particular point. This is the cosmological principle. The universe is homogeneous and isotropic on large scales, meaning it has no preferred location and no preferred direction. We are not at the center, because there is no center. Every observer, in every galaxy, in every cluster, in every supercluster, sees essentially the same universe, the same web, the same expansion, the same horizon. From the Andromeda Galaxy, astronomers would observe the same cosmic web we see, just from a vantage point 2.5 million light-years different. From a galaxy at the edge of our observable universe, looking back toward the Milky Way, astronomers would see a universe expanding in ways that looked identical to what we observe here. The geometry of the universe, whether it is flat, positively curved like a sphere, or negatively curved like a saddle, has been measured with great precision using the CMB. The answer is flat, or so close to flat that any curvature is below detection. A flat universe is geometrically consistent with infinite extent, though we can observe only the finite observable patch within our horizon. In an infinite universe, every possible arrangement of matter occurs somewhere, not out of mysticism, but out of statistics. If you have infinite volume and finite scale structures, every configuration recurs. The question of how large the total universe is, whether it is truly infinite or merely vast, is one that current physics cannot answer. What it can say is that what we have mapped, the entire observable universe, galaxies from the first 280 million years of cosmic time to the present, structures stretching from single stars to filaments spanning 1 billion light-years, is not the whole story. It is the visible chapter of a much longer book, written in the language of gravity and dark energy and quantum mechanics, still being read. Outro. We began this journey inside a single barred spiral galaxy, 26,000 light-years from its center, on a rocky planet so small that no instrument yet built can resolve it from the distance of the nearest large galaxy cluster. We traveled outward through the local group, through the Virgo cluster, through the 520 million light-year supercluster we call home, through the tangled threads of the cosmic web, past thousands of galaxy clusters and hundreds of billions of galaxies, all the way to the edge of what light has had time to show us. We met galaxies born 280 million years after the Big Bang, still blazing with their first generation of stars. We passed through voids 330 million light-years across. We learned that half the ordinary matter in the universe is not in galaxies at all, but in a hot, thin gas filling the spaces between them. A cosmic supply chain that fed the entire history of stellar creation. What this journey shows is that the universe is not a collection of separate objects, but a single, interconnected structure. Matter organized by physics into patterns that repeat and vary across 13.8 billion years of history. Every galaxy we passed is connected to every other by the web of dark matter and gas that runs between them. Every atom in every star was forged in a previous star's core and scattered by that star's death. Every massive black hole at every galaxy's center grew through the same accretion processes that also build the stars around it. There are no isolated things in the universe. There is only the universe, expressing itself at different scales and different moments in time. It is also a universe that is not finished. The most distant galaxies JWST is finding are still in the process of their first generations of stars. The great galaxy clusters are still accreting matter from surrounding filaments. The Milky Way is still absorbing small satellite galaxies. Andromeda is still approaching. The cosmic web is still evolving, its voids growing emptier and its nodes growing denser. The future is as long as the past has been, and the universe will look profoundly different in another 10, billion years. What we have mapped is a snapshot of a middle chapter, one particular moment in a process that has no obvious end. And the remarkable thing, the thing that justifies this entire journey, is that a species on one small rocky planet, around one ordinary star, in one average spiral galaxy, in one node of the cosmic web, figured most of this out. Not through any special access or cosmic privilege, but through careful accumulation of evidence, instrument by instrument, survey by survey, question by question. The universe gave nothing away. We earned every light year of it. If you found this journey worth taking, there is more where it came from. Subscribe, and we will keep going.